So hello and welcome to our third session. So this time we are going to continue with our discussion on the types of loading. So previously we had discussed on the codes, formulas, factors, and calculations involving dead loads, live loads, a little bit of highway bridge loads, railroad bridge loads, and impact loads, more on wind load calculations on our examples. So today we will have the snow loads, earthquake loads, hydrostatic and soil pressure. So we'll just focus on what is on the relevant codes, such as National Structural Code of the Philippines and Uniform Building Code, or UBC 1996, and a sort of ASCE 7-10. We will not go deeper into its details because these topics are tackled more on your earthquake engineering as well as hydraulics and geotechnical engineering. Basically, snow loads are not so much concerned in our country because at least we should have a knowledge on that snow loads. So for snow loads, of course, it is a roof loading due to snow, as we perceive that snow will be accumulated on the roofing. So basically, our design loadings is associated on general shape, roof geometry, the wind exposure location, its importance, or whether or not it is heated. Okay, so as usual, the American Society of Civil Engineers will provide us some important codes relating to snow loads, although in our country we do not have any instances of snow. So for the zone map, it reflects a loading based from reporting a 50-year recurrence intervals of an extreme snow load. So although ASCE 7-10 does not contain a more in-depth data on snow loads, at least we have this zone map for the snow loads. Further, the empirical formula for a flat roof is provided on the same ASCE 7-10, which relates to, just similar to wind load, we have an exposure factor which will depend upon the terrain. For a fully exposed roof, okay, in an unobstructed area, for example, we have a value of 0.8, whereas if the roof is sheltered or located in the center of a large city, then we have a CE of 1.2. So another factor is a thermal factor, which refers to the average temperature within the building. So it considers also temperature. For unheated structures kept below freezing, we have a thermal factor of 1.2. And whenever if the roof is supporting a normally heated structure, we have a CT of 1.0. So another factor, this is a similar factor for an earthquake loading that will be introduced by and by. the importance factor relates to occupancy. So there are different factors according to occupancy. For example, if we have an agriculture and storage facilities, it will have a 0.8 importance factor for that, much higher for an occupancy for schools and hospitals, which is pegged at 1.2. So we will not go into deeper knowledge with regards to snow loads because, as I have said, it is not much of concern in our country. But at least when you practice later on and decide to work on Europe or American countries or in the West, at least you should know the reference where to find these snow loads. Okay? So, another type of load is an earthquake load. Of course, it is normally termed as seismic loading. So, seismic loading is one of the basic concepts of earthquake engineering, which means applications of an earthquake-generated agitation. So, how would a structure will behave when there is a ground shaking? So this seismic loading will be converted into a lateral force that is applied on the frame of a certain building structure. So it happens at contact surfaces of a structure either with the ground or with adjacent structures or with gravity waves from tsunami. Seismic loading depends primarily on anticipated earthquake parameters at the site known as seismic hazards, geotechnical parameters of the site, structures parameters, characteristics of the anticipated gravity waves from tsunami if applicable. Okay. So, again, we will not go into details, but we would like also to present where to get these values or where to get the codes or the relevant codes pertaining to the earthquake loads. As I have said, this will be tackled in depth in your earthquake engineering subject later on. So, the National Structural Code of the Philippines will provide us with Section 208, which contains all you need regarding earthquake loads. Okay, so Section 285.1.5.11.2 contains the detailing requirements in Zone 4. So in our country, this is subdivided into zones of earthquake, because reiterating that the Philippines is located within the ring of fire of our earth latitude. So therefore, this an earthquake prone country. Similarly to adjacent countries like Japan, actually Japan has a very good criteria with regards to in dealing with earthquake engineering. Okay, so another section 285.1, we have a simplified static force procedure, which further contains horizontal distribution and vertical distribution. Another section contains static force procedure in section 208.5.2, which includes design based shear, structure period, so elastic fundamental period of vibration direction under consideration. So normally under this structure period T, it has two methods under this section. We have method A and method B. So finally, we have section 5.3, the dynamic analysis procedure. So in general, we have two basic analysis in seismic analysis or earthquake loading. We have static and dynamic analysis. So under static and dynamic, we have linear and nonlinear distribution of earthquake loading. Okay. So as a loading, we have the so-called base shear. So base shear is actually the maximum lateral force that will occur due to seismic ground motion at the base of the structure. So it is denoted by capital letter V, equivalent to CV IW all over RT. So this was originally adopted by NSCP equation 208-8 from Uniform Building Code 1997. So for the variables, we have CV as seismic coefficient. So this is based generally on the soil type as well as the seismic zone. So CV is best to be referred on NSCP because NSCP is on the Philippine setting. So it is impractical to use a code that is not within our place. Okay. So next we have I. I is a seismic importance factor. Like in the snow load we have introduced a while ago. Residential versus hospital is an example wherein hospital has a greater seismic importance factor comparing to the residential, to that of the residential. Okay, so for the next variable we have R, the response modification factor. So it depends on the type of the building, whether the building is a structure of steel frame, or it could be a reinforced concrete, or it could be a combined one. Okay, so we have a table on NSCP. So another variable is the T, seismic time period of the structure, which was introduced a while ago. We have actually method A and method B in order to determine the seismic time period of the structure. And for the last, we have W, the total dead load of the structure. So essentially we have a calculation of dead load on the previous topics, or on the previous topic we had. So that is actually a prerequisite in earthquake analysis of the structure. So you should have to master how to determine the dead load of the structure. So as for the tables and equations provided by section 208, for the seismic coefficient according to soil type and seismic zone, there are a lot of tables pertaining to that CV. First, we have 208-2. It refers to the soil type, or the table for the soil type. Okay, whether the soil type is a stiff or a soft soil, etc. Okay, so table 208-3, we have seismic zone factor. In the Philippines, we have the so-called zone map for, or the referring to the seismic zone factor, zone map in the Philippines, contained in NSCP table 2, section 208. Okay, so in particular we have the table for the seismic zone factor. So another table we have near source factor NA in 208-5, and another table for 208-6. So the near source factor NV. So near source factor just refers to the factor how far is your structure or the site from a nearest fault line on the map. Okay, whether it is greater than 15 kilometers, less than 15 kilometers, etc. Okay, so table 208-7 also contained seismic coefficient CA, and 208-8 we have seismic coefficient CV. So for the importance factor, it contained in table 208-1, okay? And R will be found in 208-11A, the earthquake force resisting structural systems of concrete, and another table that is 208-11B for earthquake force resisting structural systems of steel. So again, we have the seismic time period of the structure. We have method A, equation 208-12, and method B, equation 208-14. So at least you have a reference or where to find these codes pertaining to earthquake engineering and earthquake criteria or on seismic analysis here in the Philippines, in our country. So again, we will not go into a depth to an in-depth analysis on that, because this is a separate topic for your curriculum. Okay, so as we can see here, perhaps we can have this to be hydrostatic and soil pressure. Hydrostatic and soil